Welcome to Science After Dark. You know that very specific feeling when you're filling out an online form and it asks for your address, you type in your street, your city, your state, and then you hit that drop-down menu for your country.
Right. It's the final bounding box for where you exist on the planet.
Yeah, exactly. But imagine if that drop-down menu just kept going. Past your country, past the planet, past the solar system, out into the cosmic web, all the way to, the absolute limit of the observable universe. We are mapping out your exact cosmic address.
And the goal here isn't just to barrage you with increasingly larger numbers until the scale becomes completely meaningless. It's about unpacking the underlying physical laws. We want to look at how humanity managed to map billions of light years of space without physically leaving our own, tiny celestial backyard.
Okay, let's unpack this, because to understand the cosmic web, you really have to grasp the fragility of the ground beneath your feet. We need to shrink the Earth, which is roughly 12,700 kilometers across, down to the size of a standard glass marble you could hold between your thumb and index finger.
When you scale the Earth down to a marble, it forces a pretty radical shift in how you view our atmosphere. A lot of people picture it as a thick, protective bumper.
Right.
But on the marble scale, the atmosphere isn't a bumper at all. It's just a microscopic film of moisture on the glass. Every cloud, every commercial airplane, every living organism exists within that impossibly thin, delicate smear.
Which raises the question of how it even stays there. I mean, why doesn't the solar wind just strip that thin film away?
Well, that comes down to habitability being an active, dynamic engine, not just a static state of, being a rock with water. Deep inside that marble, you have a dense, rotating metallic core acting as a dynamo.
Generating the magnetic field.
Exactly. That field deflects the charged particles of the solar wind. And above the core, you have a mantle of convecting rock that drives plate tectonics, which literally recycles carbon into and out of the atmosphere over geological timespans to regulate global temperatures.
So liquid water isn't just a lucky feature, it's the result of a planet-wide thermodynamic system perfectly balancing atmospheric pressure and heat distribution.
And the margin for error is razor thin.
Yeah, it really is. Let's apply the scale to human achievement, actually. The International Space Station operates at about 400 kilometers up. On our marble scale, the ISS is skimming a fraction of a single millimeter above the surface of the glass.
It's barely off the ground.
Right. And this highlights a pretty big misconception about orbital mechanics. You see astronauts floating on the ISS, and the immediate thought is, oh, they're in zero gravity. But Earth's gravity at 400 kilometers up is still roughly 90% as strong as it is on the surface.
They are experiencing microgravity, but not because gravity is absent. They're just in a state of continuous freefall.
Falling sideways, essentially.
Exactly. The mechanism of an orbit requires the spacecraft to move laterally so incredibly fast, roughly 28,000 kilometers per hour, that as gravity pulls them down, the curvature of the Earth simply falls away beneath them at the exact same rate. They are perpetually missing the ground.
And it's fascinating that humanity deduced the scale of the planet they were falling around long before we ever had the technology to leave the ground. I mean, Eratosthenes didn't need a satellite over 2 millennia ago.
No, he just needed a fundamental understanding of geometry and solar radiation. By measuring the slight difference in the angle of shadows cast in 2 different Egyptian cities on the summer solstice, he extrapolated the curvature of the entire globe.
It's such a great example of deducing massive cosmic truths from tiny local data points.
Which is exactly what we have to do when we look beyond Earth, because our physical reach is, well, it's stunningly small.
Yeah, let's look at the moon. On our marble scale, the moon is a smaller bead located about 1 meter or 3 feet away.
And that single meter of empty space is vast enough that you could line up every other major planet in our solar system side by side in that gap.
Which is wild. And the Apollo footprints on that bead represent the absolute limit of human physical travel. We haven't sent a person further than that 1 meter.
And when you look at the moon tidally locked, lacking in atmosphere, constantly bombarded by radiation, it begs a serious question. Why is Earth this thriving thermodynamic engine while our immediate neighbors are completely hostile?
Right, and this challenges the traditional concept of the Goldilocks zone. We hear this term constantly, implying that distance from the sun is the ultimate key to life. But Venus and Mars are technically in or very near that habitable zone.
Yes.
I mean, Venus is almost Earth's exact size, yet it has surface temperatures hot enough to melt lead.
If we connect this to the bigger picture, distance from a star is merely a prerequisite for liquid water, not a guarantee. Venus experienced a runaway greenhouse mechanism. Without plate tectonics to sequester carbon, its atmosphere thickened to the point where it trapped more solar heat than it could radio back into space.
The oceans just boiled.
Right, which put more water vapor, a very potent greenhouse gas, into the air, compounding the cycle until it became a pressure cooker.
And Mars went the other direction. We have the geological data proving it once had flowing water, but its core cooled. It lost that internal dynamo, the magnetic field shut down, and the solar wind stripped its atmosphere away into deep space.
This is why the term Earth-like in astronomical press releases can be highly misleading.
Oh, absolutely. The data shows that just because a newly discovered exoplanet is rocky and in a habitable zone, it doesn't mean you can breathe there. Like, what if it orbits a red dwarf?
That completely changes the physics. Red dwarfs are cooler, meaning a planet has to orbit much closer to stay warm. But orbiting that close means the gravitational gradient across the planet is severe, leading to tidal locking.
One side permanently faces the star in blistering heat.
And the other faces the cosmos in frozen darkness. Add in the fact that red dwarfs are notoriously volatile and emit massive stellar flares, and that, Earth-like planet is likely just a sterilized rock.
So if traditional planets in the habitable zone are this fragile, we have to look at a paradigm shift. The gas giants in our own solar system, Jupiter and Saturn, they don't even have solid surfaces.
But their moons do. Take Europa or Enceladus. They exist in the freezing depths of the outer solar system, far beyond the traditional Goldilocks zone.
Yet we have data showing Enceladus literally blasting plumes of liquid water out into space.
Because of tidal heating. These moons are caught in an orbital tug-of-war. The massive gravity of the gas giant pulls them, but the gravity of neighboring moons pulls them the other way.
So they're just getting stretched.
Physically stretched and squeezed. Yes, as they move in slightly elliptical orbits. That immense internal friction generates heat, maintaining vast global liquid oceans beneath miles of surface ice.
So we have the potential for life in environments we previously assumed were dead, frozen wastes. But mapping these mechanics in our solar system is one thing. How are we doing this for exoplanets orbiting entirely different stars?
Well, we have to comprehend the scale jump first. If the sun is an exercise ball sitting in a room, Earth is a peppercorn about 25 meters away.
And the nearest star system, Alpha Centauri.
On that scale, the next exercise ball is thousands of kilometers away.
Which means we are not visiting these places. The Voyager probes have technically crossed the heliopause, pushing past the solar wind in interstellar space. But after decades of travel, they are still less than a single light day away.
Right, so we have to detect exoplanets strictly by analyzing light. The most common way is the transit method.
There's a great analogy for this. It's like staring at a massive, blinding stadium floodlight from miles away and trying to detect a moth flying in front of it. But frankly, I look at that analogy and wonder, is the dimming really that detectable? A moth against a floodlight seems impossible for a telescope to catch.
It requires extreme precision, but yes. We aren't looking for a shadow exactly. We are measuring the overall photometric light curve of the star. When a planet transits, it blocks a microscopic fraction of a percentage of the star's light.
And if that dip repeats?
If it repeats at a regular, predictable interval, we can infer a planet's orbit and size.
And we pair that with the radial velocity method, right? Looking for the wobble.
Precisely because gravity is a two-way street. The star pulls on the planet, but the planet pulls back. They actually orbit a shared center of mass called a barycenter. This causes the star to wobble slightly.
And that changes the light we see.
Yes. As it wobbles toward us, its light waves compress and shift toward the blue end of the spectrum. As it wobbles away, the waves stretch toward the red.
But detecting the planet is just the first step. The part that really stands out is spectroscopy. How do we know what is in the atmosphere of a planet trillions of miles away?
We let the universe do the chemistry lab work for us. When a planet transits its star, a tiny fraction of that starlight passes through the planet's atmosphere before continuing on to Earth.
And the gases in that atmosphere interact with the light.
At a quantum level, atoms and molecules have very specific energy states. When photons of light hit a molecule of, say, methane, the electrons in that molecule absorb specific wavelengths of light to jump to a higher energy state.
So when the rest of that starlight finally reaches our telescopes, we spread it out into a spectrum and we see gaps. Missing lines where that specific light was absorbed. It's literally a barcode of the planet's chemical makeup.
Exactly. We can deduce the presence of water vapor, carbon dioxide, or oxygen without ever seeing the planet itself. But to read that light accurately, we have to deeply understand the star emitting it.
Right, because stars are not uniform campfires. Our sun is a G-type main sequence star, a yellow dwarf.
Astronomers classify stars based on their mass, which directly dictates their core temperature, fusion rate, and lifespan. The classification system uses letters O, B, A, F, G, K, M.
The O-type stars are the massive, insanely hot blue giants.
And because they are so massive, their gravity creates immense internal pressure. They burn through their nuclear fuel in a few million years. Contrast that with M-type red dwarfs, which have such low mass they just sip their fuel and can burn for trillions of years.
But we owe our existence to the massive stars that burn out quickly and die violently. A star spends its life fusing lighter elements into heavier ones, pushing outward with radiation pressure to combat the crushing inward pull of its own gravity.
Yes, but once a massive star fuses elements all the way up to iron, the physics break down. Fusing iron consumes energy rather than releasing it.
So the engine stops.
The outward radiation pressure drops to zero, and the entire mass of the star collapses inward at a significant fraction of the speed of light. It hits the core, bounces, and triggers a supernova.
And the sheer energetic violence of that explosion is what forges the elements heavier than iron. The oxygen you breathe, the calcium in your bones, the iron in your blood, those were all forged in the death throes of massive stars and scattered across the galaxy.
We are entirely constructed from stellar exhaust. But the remnants left behind by these dead stars push the limits of physics. If a star is small enough, the collapsing core stops when the electrons are packed so tightly they physically cannot share the same quantum state.
The electron degeneracy pressure.
Right. That holds up a white dwarf, an object the size of Earth but containing half the mass of the Sun.
But if the star is more massive, gravity overpowers the electrons. It crushes the electrons and protons together to form neutrons,
resulting in a neutron star. City-sized, but with a mass of multiple suns, supported entirely by the resistance of neutrons being squeezed together.
And if the star is even more massive, nothing stops the collapse. It forms a black hole. Now, this is where we have to push back against a major pop culture trope. Black holes are almost always portrayed as cosmic vacuum cleaners, aggressively sucking up everything in the universe. But if you replaced our sun with a black hole of the exact same mass, the Earth wouldn't get sucked in. It would just continue orbiting in the freezing dark.
What's fascinating here is the mechanism of a black hole isn't a vacuum. It's just localized extreme gravity. It is a region where mass is compacted so densely that it severely warps space-time.
And the boundary of that warping is the event horizon.
The Schwarzschild radius. If you cross that boundary, space is curved so severely that the velocity required to escape exceeds the speed of light. And since nothing can travel faster than light in a vacuum, nothing escapes.
So if no light or information can escape, how are we mapping them?
By the extreme friction they cause in their immediate environment. When gas or stellar material spirals toward a supermassive black hole, conservation of angular momentum flattens it into an accretion disk.
And that material is moving fast.
Incredibly fast. The particles are rubbing against each other, generating friction that heats the disk to millions of degrees.
These are quasars. We are seeing the superheated materials screaming just outside the event horizon before it crosses over.
We also detect them through gravitational waves. When two black holes merge, they violently displace mass, sending literal ripples through the fabric of space-time. The LEGO observatories detect these events by measuring the microscopic stretching and squeezing of space itself right here on Earth.
It's incredible, but everything we've mapped so far, the exoplanets, the supernovae, the black holes, it's all happening inside our specific galaxy.
The Milky Way, a barred spiral galaxy containing hundreds of billions of stars.
And our cosmic address within it is actually quite privileged. We are in the Orion Spur, about 26,000 light years from the galactic center.
Which is the galactic habitable zone. You do not want to be near the center. It's highly dense, flooded with lethal radiation from frequent supernovae, and anchored by Sagittarius A star, our supermassive black hole. Out here in the suburbs, our solar system can remain stable for billions of years.
Zooming out further, the Milky Way is part of the local group. It's a relatively quiet neighborhood. We have the Milky Way and Andromeda as the two massive anchors, the Triangulum Galaxy, and a smattering of dwarf galaxies.
But studying the movement of galaxies in larger clusters is what led to one of the most unusual discoveries in astronomy. In the 1930s, Fritz Zwicky analyzed the Coma cluster, which contains over 1,000 galaxies. He measured their velocity dispersion, basically how fast they were moving around the cluster's center.
And the numbers didn't add up.
They were moving far too fast. Based on the gravitational pull of all the visible matter stars, gas, dust, the galaxies should have been flying apart into deep space. The cluster shouldn't have been able to hold itself together.
So there had to be an unseen source of immense gravity acting as the glue, dark matter.
We still don't know the specific particle physics of dark matter, but we can map its macroscopic effects. We observe how its mass bends the light of background galaxies' gravitational lensing.
And we use something called galactic redshift to map this dark matter into the cosmic web. But how does measuring light tell us where these structures are in 3D space?
Well, this requires distinguishing between the local Doppler shift we talked about with exoplanets and cosmological redshift. The universe itself is expanding. As light travels across expanding space to reach us, the space beneath the light wave stretches, which stretches the wavelength of the light itself toward the red end of the spectrum.
So the further away a galaxy is, the more space the light had to travel through, the more the space stretched, and the redder the light appears.
Exactly. By measuring that redshift, we map the distance of millions of galaxies, and we find they aren't scattered randomly. They trace the underlying structure of dark matter. Massive glowing filaments and broadsheets strung across the universe, separated by staggeringly large empty voids.
Wait, if the universe is expanding and space itself is stretching, why aren't we being stretched? Why isn't the distance between the Earth and the Sun, or the stars in the Milky Way, expanding?
It comes down to the battle of fundamental forces. The expansion of space is happening everywhere. But locally, gravity easily overpowers it. The gravitational binding energy holding the solar system together, or the Milky Way together, is orders of magnitude stronger than the gentle outward pressure of cosmic expansion.
So expansion only wins in those massive empty voids between the galaxy clusters where gravity is weakest?
That is the domain of dark energy. While dark matter acts as the gravitational scaffolding pulling structure together, dark energy is the mechanism driving the accelerated expansion of the empty space, pushing the large-scale structures further apart.
And because space is expanding, it creates a bizarre mathematical reality at the very edge of our cosmic address. We know the universe is roughly 13.8 billion years old. So you'd think the furthest we could see is 13.8 billion light years in any direction.
But the observable universe is actually about 93 billion light years across.
Because while the light from those distant points was traveling toward us for 13.8 billion years, the space it was traveling through was continuously expanding. The location that emitted that light has been pushed tens of billions of light years away from us in the meantime.
The oldest light we can detect is the cosmic microwave background.
The CMB.
Right. About 380,000 years after the Big Bang, the universe finally cooled enough during the recombination epoch for electrons to bind to protons. This allowed photons, which were previously trapped in a dense, opaque plasma, to finally fly free. The CMB is that first burst of light, stretched by billions of years of expansion into microwaves.
But the CMB isn't a physical wall. It's not a brick boundary where space stops.
It is a horizon in time. The edge of the observable universe is simply the absolute limit of how far light has had time to travel to reach our instruments since the universe began. It is not the edge of reality, it is merely the edge of our information.
The edge of our information. That is a striking way to look at it. We have mapped out this massive cosmic address, starting from the fragile thermodynamic engine of our planetary marble, looking out past the frozen, tidally heated oceans of our outer solar system, using the microscopic dimming of light to read the atmospheric chemistry of worlds we will never visit, tracing the violent stellar alchemy that forged our bodies, out through the gravitational chaos of black holes, into the Orion Spur, and across a 93 billion light-year web of dark matter scaffolding.
And astronomy achieved all of this deduction without ever physically leaving our immediate neighborhood. We are simply capturing and interpreting the light and gravity that happen to wash over our tiny world.
Which means this address is incredibly intimate. You, listening to this right now, are bound by the exact same physics holding the coma cluster together. The atoms currently firing in your brain to process this information were forged in the core collapse of a dying star. You are quite literally the universe's mechanism for understanding itself.
Being physically small does not equate to being insignificant when you are part of the system.
It certainly doesn't. And I want to leave you with one final thought to process. If the edge of the observable universe is merely a temporal horizon, an optical illusion dictated by the speed of light and the ongoing stretching of space, imagine what lies beyond it. Imagine what massive, unseeable superstructures and galactic webs are currently drifting just over that horizon, forever expanding outward at speeds faster than light can traverse, permanently beyond our reach in the unobservable universe. Just sitting there, completely real, but forever off the edge of your drop-down menu. This is Science After Dark, signing out.